All right, well, good morning, everyone. It's a pleasure to introduce McKenzie Carlson. So McKenzie is a second-year PhD student who's working with Laura Wallace and me on a joint project uh, using offshore geodetic tools. So this is to try to monitor the deformation of the Earth's crust off the coast of New Zealand in the subduction zone there. In particular, using data from two borehole observatories that were installed now a little more than 6 years ago, believe it or not. So this really cool data set, and she's done some really exciting work trying to figure out, kind of monitor what we like to think of as like the creaks and groans of Earth's tectonic plates with these really sensitive instruments, and put that together and to understand how that tells us about the dynamics of subduction.
All right, can you hear me through the mic? Awesome. Thanks, Damien, for the introduction. Again, my name is McKenzie. I'm a PhD student here at UTIG. And yeah, as Damien mentioned, I'm going to talk to you about a triggered slow slip event that we observed in the Hikurangi subduction zone using IODP borehole observatories. The northern Hikurangi subduction zone is off the east coast of the North Island of New Zealand, and it is well known for its large, frequent, and shallow slow slip events. Because of this, it was the target of IODP expeditions 372 and 375 in order to core, log, and install two borehole observatories. And as Damien mentioned, these are really good at helping us understand the offshore environment, because prior to this, most of the slow slip events were recorded just on onshore GPS, which is great, but they don't do as good a job in the offshore region. So these two borehole sites were installed. We've got site U1518, it's about 5 kilometers from the trench there, and then site U1519, which is about 35 kilometers landward of the trench. They were installed in 2018, and the last time data were recovered was in 2023, so we've got about 5 years worth of data from these borehole sites. They're recording temperature and pore fluid pressure data. I'm going to be just focusing on the pore fluid pressure data in my talk today. This is what the borehole observatories look like. So they're installed in the seafloor, and they're really great for measuring really small changes in pressure due to tectonic events. And they are great because at the Cork, they have a pressure sensor on the seafloor that's measuring pressure changes due to the overlying oceanography, so the tides and any other pressure changes that might be going on. And then at each site, you have 2 or 3 downhole intervals that are sensing the pore fluid pressure in the formation. So the top sensor is just sensing what's going on in the ocean, and then the bottom sensor is sensing what's going on in the formation, but it's also recording those changes in pressure due to the oceanography. So as you can see in this plot, the dominant signal here is the ocean tide, and this completely dwarfs any pressure change signal we might be interested in. You can see the tide pressure changes are on the order of 10 kilopascals every day, but things we're interested in are fractions of a kilopascal. So we want to be able to get rid of this noise from the ocean tide and any other oceanography. And because these pressure sensors are co-located, it's pretty simple to just scale down the wellhead pressure and remove it from the downhole pressure, and you're left with just the things that are going on due to tectonics. And so that's what it looks like once you have removed the oceanography. And so now you can see our changes in pressure are fractions of a kilopascal instead. So it's really good at sensing really sensitive changes in pressure. We're interested in measuring changes in pressure because we can use pressure as a proxy for volumetric strain. So if you squeeze the rock, the pressure in the formation is going to go up. If you stretch the rock, the pressure in the formation is going to go down. And we want to be able to figure out what the volumetric strain is, so that we can put that into our models to figure out how much and where slip is happening on the fault. So we're able to use some simple equations to create this conversion factor. It's using material properties of the rocks. We did some lab experiments to determine those. And you can see that the conversion factors are slightly different between the two sites, but that's just due to the fact that they have slightly different material properties. So now that we've removed all of the oceanography, here's our time series of data. This is about 3 years worth of the pore pressure data. At the top, you've got site U1518. Again, that's the site nearest to the trench. In the middle is the other borehole site, 1519. And then for reference on the bottom, I've put the closest onshore GPS site. So we can see there's lots of pore pressure transients throughout the time series that correlate to slow slip events. And most of these transients in the borehole observatories correlate really well with slow slip signals that we see in the onshore GPS. There is one notable exception, however, that occurred in early 2021 after this magnitude 7.3 East Cape earthquake that occurred just north of New Zealand. And if we zoom into this event, so again, there's that magnitude 7.3 East Cape earthquake. This was part of a kind of series of earthquakes that were happening in the New Zealand region. A few hours after this earthquake, there were two other earthquakes farther north in the Kermadec Trench, but we see a big spike in pressure right at the earthquake. And then after that, a large pressure transient at site 1518 on the order of 2 kilopascals. We also see some signal at site 1519. It's not quite as dramatic, but it's still there. But the key here is that we don't see anything going on in the GPS. Again, that's the one on the bottom, or even seafloor pressure sensors. So that's the third one down there is the wellhead pressure corrected for oceanography. And you don't see anything going on at either of those two, either of those two types of data, but it's picked up really well by the downhole pressure in the boreholes. So in order to figure out how much slip is occurring during this event and where it's happening, I do an inversion using some Green's functions. And I do that by splitting the event up into 3 stages and then doing a static conversion during each stage. And I have split the event into 3 stages based on what's going on at site 1518. So we can kind of see in that top plot here, initially at both sites, you're in extension because we see that pressure decrease. And then as you progress through the event, it switches to compressional at 1518 because we see that pressure increase. You're still in extension at the other borehole site. And then a little bit later in the event, we see perhaps a change of slope in what's going on at 1518, and then kind of a lapse in any signal at 1519, or perhaps a slight bit of compression. And again, no signal at all in the other types of data. To figure out the amount of slip and where it's happening, as I mentioned, I do just a pretty simple weighted non-negative least squares inversion using Green's functions that relate slip on 10-kilometer patches along the fault to strain in the boreholes or displacement at the GPS sites. These Green's functions are generated using Pilith. It's a crustal deformation modeling software, and it's constrained by realistic elastic properties in the offshore region from the New Zealand seismic velocity model and some information from logging well drilling data from the IODP expeditions. And this is really key because the borehole sites are really sensitive to changes in material properties. So you kind of have to use this more heterogeneous material property in your model in order to get an accurate representation of what's going on. So here's my results. Looking at this figure, we're kind of stepping our way through those 3 stages of the event I've defined to see how much slip is going on and where. So on the right-hand side of the plot, at 0, you're at the trench, and then going to the left, you're going landward. And so we see that during the first stage of the event in yellow there, we see a kind of a broad range of slip a couple tens of kilometers away from the trench. As we go into the next stage, we see the slip kind of expand and also move towards the trench. And then by the time you get to the last stage of the event, you're slipping just at the trench in those nearest couple tens of kilometers. And when we run the forward model using these slip results, we see that our changes in pressure are pretty well fit by this slip model. So we're doing a decent job at capturing what might be going on. So to conclude, I just want to point out that the borehole observatories are a really great tool for understanding what's going on in the offshore region. I talked about this slow slip event that was completely invisible to any of the onshore GPS sites. We also show that during this event, the slip originated near and migrated towards the trench. So we're capturing what's going on in the near trench region. And then this observation also supports the idea that shallow slow slip events are susceptible to dynamic triggering, which has been proposed before. And then also finally that incorporating heterogeneous material properties into your deformation models is really important, particularly offshore. So thanks for listening, and I'm happy to take any questions.
Thorsten. Plot that shows that the lateral variations in elastic properties matter?
I don't have a plot that shows it, and I haven't actually, Laura has a paper.
I know, but I mean, it's not really your conclusion then, right?
Right, yeah.
And if you're doing that, are you double dipping when you have different conversion factors between strain and pressure? Or why are those different? Are those different Because of site conditions or something in the instrument?
They're different because of the material properties of the rock, like the site conditions. So you have slightly different like compressibilities and porosities of the rocks at each site. And so that is what goes into your pressure to strain conversion. And so they're slightly different between the two.
And is that a completely different scale then from the variations you're putting in here?
I think the logging wall drilling data is incorporated into the changes in material properties in the pilot model. So
are you double dipping then or not? Are you already correcting for site conditions, but then you're using Green's functions that have site conditions in them?
I don't know.
You want an answer or?
Yeah, both, right? I mean, people will ask,
Yeah,
right? So
Damon, do you want to?
Really good question.
Yeah.
All right, I'll jump in because I mean, it's a really good question. So the Green's functions get you from impulse to strain.
Right.
And that is part A of this. And that you need the heterogeneous properties, right? Part B is when you want to turn the strain into a pressure that you observe locally at the borehole. So it's not double dipping. It's like a signal conversion piece is the pressure to strain. But then the large scale response of a remote impulse and what that does in terms of the strain signal locally, that's where you need the heterogeneous properties in the Green's function. So it's, in other words, if she had strain meters rather than pore pressure, she wouldn't have to do the conversion and you still need the heterogeneous properties, right? So it's not double dipping, it's sequential. No. You mean, why do you need the heterogeneous properties? Yeah, so I mean, I have applauded this too for Japan, and it's, you can look at an Okada solution and you can compare the Green's functions for the Okada solution with something that has realistic properties, and it's a factor of 3 different in some places, so it just depends. So that's, I totally agree, that's not the conclusion of this work. Yeah, it's a good point. Like, be careful about saying that's your conclusion if it's just kind of something you did.
Right.
Because you're not, you didn't do this talk isn't about that topic, right?
I might have just missed it, but what is dynamic triggering?
It's basically triggering from the changes in stress due to the passing like earthquake waves instead
Okay,
of
thanks.
like just changes in stress after the.
Gotcha. We need to move on to the next goal.
Sorry, Thorsten.
Okay, so Medha joined us from the University of Virginia. She's with us here in her second year of PhD, right? At University of Virginia, the experience she got from that is to writing a paper right now, right, on A-scales, a comparison of A-scales, which are those subglacial structures that you can find on Earth and Mars. And she's doing these kind of analog comparisons. But she's here with us for something completely different, which is on the moon. So she knows the Earth, Mars, and the moon, right? Where she studies the geologic context of the Schrödinger Basin, which is a giant crater in the south pole of the moon that has a lot of similarities in its formation process and structure with the Chicxulub crater on Earth. So she works with Sean, Mercedes, and myself to make some geologic context of this, because it's going to be a target for landing missions on the moon in the near future. Yeah, here we go. Up to you.
Can you guys hear me? Is this good? Amazing, because I can't tell. Anyways, so thank you for the introduction, Cyril. So I'm Medha. I'm a second year PhD student over here, and I love everything about space. So I'm excited to talk to you about my work investigating the impact materials in Schrödinger Basin. So generally for context, impact cratering is the dominant surface process of the moon. We think it's this very serene thing, but it's actually subject to this constant bombardment of material from space. And so you can say that the moon is primarily composed of materials generated by impact processes and the ensuing volcanic processes that sort of happen with it. And so this is the far side of the moon, and I'm going to take you guys to the lunar South Pole, to Schrödinger Basin. And really, it's a sort of microcosm of these processes. So this is a map. Oh, well, this got diluted really weird. Anyways, This is a map of radar reflectivity in Schrödinger Basin, where the purple shows relatively radar rough areas and the yellow areas show relatively radar smooth areas. And you can really see a lot of different types of materials locally in this basin. Over here, you might see deep crustal material excavated by the impact process. You might see volcanic flows. You can also see more recent impact ejecta that happened from Copernican craters. And you can also see explosive volcanism evidence through the rough pyroclastic deposit. But the question still sort of remains, what is the major stratigraphy of the basin and what primarily composes the crater floor? And so on Earth, we can take some inspiration where you can experience these crater floors on Earth that are composed of materials that are subject to extremely high shock pressures, generating impact melt rocks or intact impact melt sheet. But a really interesting part of the stratigraphy is breccias, because they sort of occupy this whole spectrum of characteristics, all come in all shapes and sizes. And oftentimes their depositional mechanisms are not incredibly well understood. For example, breccias that typically bear melt, or so some of that high shock material, are debated to kind of form in two major ways. One of them is a ground hugging flow. So you can imagine that all this material is sort of expanding radially outward in a crater in a sort of ignimbritic sort of flow. But also people believe that there might be some secondary explosions. The material sort of goes up in this column and then gently rains back down over the next few minutes of the impact basin. And so we can really look at Schrödinger Basin as an opportunity to understand the processes that go into composing a crater floor, because oftentimes on Earth, the crater floors are not well preserved. So we can use its morphology and remote sensing data to sort of understand the processes that go behind this. So we can learn about the stratigraphy of Schrödinger Basin and what sort of materials will future missions such as Endurance and the Draper lander encounter in the basin. We can use this as an opportunity to compare depositional mechanisms between Earth and the Moon of these materials in large impact basins. And what implications would this have for future lunar geologic missions that might go to other large impact basins on the Moon? And so to address this, I'm hoping to use topographic data derived and high resolution imagery derived from the Lunar Reconnaissance Orbiter, as well as some terrestrial analog work. And so earlier I mentioned this sort of rough, dark pyroclastic deposit. So I'm going to take you to the pyroclastic vent in the crater, and you can notice that there's this sort of really interesting bright boulder fall kind of forming a layer in the basin over here. It's relatively higher albedo. It also is present at the steepest local slope in the basin. And so we were wondering if there's some other deposits or materials in this basin that show this sort of characteristic. And indeed there is. This is an example from a graben where you can see kind of along a similar topographic profile, these remarkable outcrops and boulder falls that look relatively higher albedo compared to the rest of the surrounding terrain. And it's kind of present regardless if the site is well illuminated or not. And so in these outcrops, we see kind of this heterogeneous rubbly texture that have boulder-sized clasts that can be actually resolved by this high resolution imagery. And additionally, we see slopes of up to or above 40 degrees, which is kind of remarkable, which tells us that this is a cliff forming layer. In other words, in a layer more erosionally resistant than the surrounding regolith or whatever lies underneath. And so using those maximum minimum extents in some of these areas, we can, for example, over here in the pyroclastic deposit, it's present at around -4830 meters. And then in the graben, it's present at around -4100 meters. And so using these minimum maximum extents in certain areas of the basin, we can actually calculate a sort of thickness of this deposit. And throughout the basin, you can see that it's pretty variable, but it falls around the order of magnitude of 100 meters. Additionally, we can see that, well, Schrödinger Basin's crater floor sort of follows this natural sloping topography. And we can see that this material is also deposited in that sloping topography rather than forming an equipotential surface like we would expect for a sort of impact melt sheet when it would be liquid in its deposition. And so this could be a breccia layer. And typically in lunar impact basins, for those who don't know, usually the impact melt sheet is sort of understood as the topmost part of the stratigraphy of the basin, but we're proposing something different here based on evidence that we're seeing in our morphology. And that is because taking inspiration from Pixaloop, a very similar magnitude size structure, also peak impact basin, this breccia layer sort of blankets the entire basin and is on a similar order of magnitude of thickness. It also has textural similarities and these variable class sizes and angularity, as you can see in the cores on the left. And so this leads us to believe that this is likely a sort of polymicted, possibly melt-bearing breccia, as the volumes of melt on the moon would be produced would be far greater than any terrestrial crater. But this also begs the process of how did it get here? What is the emplacement process? So I'm going to take you to the peak ring. And so this picture doesn't really show it because the topography is sort of muted, but really the peak ring is like kilometers high. Like these are extremely big features. So to find this sort of deposit atop this feature means that it must have had to flow with really high velocity to get there. And so kind of looking at this part of the graben over here, where this peak ring where the graben is sort of cutting through, we can see these sort of dipping strata. So basically, these deposits sort of pinch off as it comes to the higher topography. And so that also implies some sort of lateral flow mechanism. And so taking inspiration from Reese Crater, kind of the original place where this sort of breccia was discovered, this polymicted melt-bearing breccia, in the seismic data done by one of Sean's students earlier, Naomi McCall, you can see that there's a similar sort of pinching up that is observed over topographic highs and an overall blanketing of this material in the crater. Additionally, if you look at it on a small scale, you can see really elongated clasts, which also implies some sort of flow mechanism. And so using this evidence, they inferred that this was likely deposited by a ground-hugging flow. And so I'm suggesting something similar for the material that we're observing in Schrödinger Basin. So basically, using remote sensing data, we are proposing that Schrödinger Basin has a pervasive variable thickness, but on the magnitude of 100 meters thick, layer analogous to a terrestrial Suevite deposited by some sort of lateral mechanism, such as a ground-hugging flow. And this is really important for the future modeling that we are doing of the basin formation. But also, interestingly, this could be really a sort of novel resource for in-situ resource utilization, because on Earth, this material is actually quarried and constructed like whole towns. And so this could be really useful for future lunar construction as well. These are my acknowledgements. Thank you to my lab group. And I acknowledge the indigenous peoples who are the stewards of the land that I work on. And yeah, I'm happy to take any questions. Thank you for listening.
Great talk. I might know the answer to this one, but any evidence for this layer in the sounding data itself?
So we took a look at the lunar radar sounding data. So in the we found a lot more clutter than we did actual signals in the data. But honestly, even the skin depth of that data is about 75 meters. So we would expect to see the layer really, really close to the surface in that radar data. But due to the clutter and also the fact that the melt rocks or the melt sheet that is deposited underneath might not have a sufficient enough dielectric contrast with that breccia layer above, we might not be able to see the interface at all if there was one.
Thank you.
Hi, Medha. Great talk. Do you think there's anything special about Schrödinger crater in particular that shows this feature, or do you think it would be widespread on the moon overall?
It's interesting because I feel like a lot of large impact basins on the moon are kind of obscured by volcanic basalts that kind of flooded over it. I would say that maybe for smaller size craters, maybe we could expect more of like that central melt sheet sort of ideal, but like I think it's very possible that other large impact basins on the moon have a similar sort of stratigraphy. I don't think Schrödinger is particularly unique unless there was something in its impact style or due to more volatiles near the South Pole and North Pole versus the dry equatorial regions, there could be difference, but I don't know.
Thank you.
All right, so now Mercedes. So Mercedes is from Texas. Mercedes did her university at UT, so she knows more than anyone else here about Texas. But she's gonna talk again about the moon. She joined us, Sean and I, for her honors thesis that she defended successfully last semester. And she did work on this precise data set, the lunar radar sonder that was orbiting the moon more than 15 years ago. It's a Japanese radar sonder. And because actually there is much more in this data set that we expected, she's still working and mining this data set right now. And you are very lucky because I think she might be, I'm not wrong, I guess, if I say she might be the only person in the world working on this data set, because the documentation is horrible. And okay, not waiting for too long, and up to you.
Much, Cyril. Yeah, so today I'm going to be talking about our work exploring the heterogeneities in lunar radar sounder surface reflectivity. So just to kind of start off, I wanted to give a brief overview of the lunar radar sounder instrument. This was on board the Kaguya spacecraft, which operated between 2007 and 2008. It transmitted a pulse at 5 megahertz frequency, its central frequency, and it had a bandwidth of 2 megahertz. It had a vertical resolution of 75 meters in vacuum and a 3.8 kilometer wide Fresnel zone. And again, we're just focused on the surface reflectivity in this work, and so we're just mapping the power of the surface echoes. And the surface echo power is going to be a combination of both the scattered and reflected power. Radar reflections are resulting from a permittivity gradient in the subsurface. This is related to density or porosity variations. And these reflections are going to come from within the first 75 meters for the surface echo of our data set. Scattered energy results from superficial roughness. And so we can definitively say that surface echo power is related or dependent on the real part of permittivity, which again is related to density and porosity and roughness. And so just some background on lunar geology. We have kind of two different terrains that we're focused on in this work, the lunar Maria terrain and lunar highlands terrain. We will focus on lunar highlands later. Right now, we're just going to be looking at lunar Maria. And so to kind of explore the materials that we're going to be looking at with this data set, we are going to be looking at Mare regolith. The regolith is a kind of thin layer, the top superficial layer in these regions. And this consists of unconsolidated material that is going to result from impact-related processes such as impact gardening. The density is pretty low, and therefore the permittivity is pretty low of the Mare regolith, although it's a little bit higher than what we would expect for the highlands regolith, which is thicker and comes from different materials, making it a little bit less dense. And then Mare basalts, these are impact-driven basaltic lava flows. These are generally classified by their titanium content and have much higher density and therefore much higher permittivity. And so because of radar's relationship to these material properties such as density, permittivity, porosity, and roughness, we can maybe use mapping of surface reflectivity to probe the material properties and structure of the near lunar surface. And so looking at our first reflectivity map, this is the lunar Maria on the near side of the moon. This is like the man in the moon, if you will. And we can see the lunar Maria kind of in blue. This is the area that we're going to be focused on today. And so looking at facies mapping on this map, just in the lunar Maria region, we can see that there's kind of two distinct facies. There's a bright facies, which has higher power, and then a medium facies, which has lower power. The difference between the bright and medium facies in terms of their power in dB is about 2 to 3 dB, depending on if you're looking at the average or the median. And so to kind of explore the heterogeneities here, we first are going to start with composition. You'll notice that this is kind of a smaller subset of the region that we looked at just a minute ago. This is kind of the region that we started with originally, and this is why my talk has a different name right now than it does on the AGU website. So looking at the iron abundance and titanium abundance against our surface reflectivity, we can see that iron is pretty much consistent across the lunar Maria terrain. However, titanium abundance appears to match really well with the surface reflectivity that we're seeing. So like higher titanium matches really well with higher surface reflectivity power. And so we wanted to do a quantitative correlation with these maps. And so we're going to mask out all of the lunar highlands so that we can just kind of focus on that lunar maria. And here I show a plot that's showing the correlation between ilmenite concentration, which is just the combination of both the TiO2 and FeO content, and the surface reflectivity power. And we can see that, these correlate pretty well. However, when we zoom out into the region that we're looking at today, this relationship doesn't really hold, and that's specifically because of Mare Tranquillitatis. So this area has really high titanium abundance, and yet it has really low surface reflectivity relative to the rest of the lunar maria. And so this begs the question, what is going on here? What's driving these heterogeneities? And so the next thing that we wanted to look at was age. Looking at age mapping of the Mare basalts versus our surface reflectivity, we can see that these correlate really well. So younger Mare basalts tend to have higher surface reflectivity. They match really well with these bright facies that we were looking at. And because surficial age has been proposed to act as a proxy for regolith thickness and the degree of cratering, which is roughness, we want to explore those parameters a little bit further. And so first, looking at regolith thickness, we wanted to model how the radar reflections will respond to difference in the layer thickness of this regolith. And so here I show one of those models where we hold the permittivity of the Mare basalt constant, and we vary the permittivity of the regolith and the layer thickness. And so looking at this plot, we can see that for pretty much every single permittivity that you can assume for the regolith, we do decrease in power as we decrease or as we increase the regolith layer thickness. And so up to a certain point at least. And so we can say, perhaps the regolith thickness could be kind of driving these heterogeneities that we're seeing in the surface echo power. However, when we look at the surface reflectivity maps against maps of regolith thickness, overall large scale roughness, which is really what's being felt by the radar, is pretty consistent in lunar maria. It's pretty much around 2 to 4 meters thick. And so, not a lot of heterogeneity there in terms of large scale regolith thickness. And so maybe it's something else that's at play here. And so the next thing that we want to look at is roughness. Here I show Armis height at 75 meters. And this map doesn't really have any correlation with the surface reflectivity in the lunar maria. It may explain some of the heterogeneity between the lunar highlands and the lunar maria, but not between that medium and bright facies that we were looking at previously. And so just some conclusions: composition, regolith thickness, and roughness alone cannot really explain the heterogeneities in surface reflectivity that we are seeing. And so we are proposing that perhaps what we're really looking at is porosity through the lens of surface reflectivity, and that perhaps the viscosity and related porosity or volatiles of these different Mare basalts across the moon in terms of age and spatially, that those have different characteristics that are kind of driving this difference in surface echo power. And also it could be that disruption events after the actual emplacement of that lava is causing fracturing, which is therefore increasing the porosity and maybe is also adding to the signal that we're seeing. And so for future work, we hope to map the surface reflectivity for the entire lunar surface. We also hope to explore the relationships between roughness, composition, regolith thickness, regolith accumulation, and surface echo power a little bit more. We would also like to explore this relationship between Mare basalt porosity and surface echo power, and conduct a thorough calibration of the LRS surface reflectivity using a 3-layer model with constraints on regolith thickness, Mare basalt permittivity, and regolith permittivity at numerous sites within the lunar maria. So that being the C5 site, C3 site, Apollo 11, and Apollo 12. And that is all of my stuff. So I will finish there and take questions.
In your correlation, it
Yes.
looked like the line didn't go through the blob.
Yeah, let me go back. There we go.
The red lines sort of should have a higher slope.
Yeah, I just use a linear regression fit in Python. So this is what it gave me. Although you also might notice that the scale on the y-axis is a little bit different than what we're looking at. I did use a different translational factor, so I need to go in and fix that at this talk. But
Yeah, is the if you use a linear regression, that assumes that you know the x perfectly well, and only the y has an error. If there's a potential error in the x, like you have two uncertain things, you need to use a different fit, and that will change the slope.
okay,
So linear regression will bias if you have an error in x.
gotcha. Okay, thank you very much.
Cool, Mercedes. So I'm not familiar with the C1 instrument, but did you compare this to, say, diviner thermal inertia type measurements?
No, not yet. We haven't done any kind of comparisons with any of those. Are you speaking specifically on regolith thickness?
Well, just the thermal inertia measurements themselves.
No, I haven't compared to any other
Okay.
data sets.
Okay, thanks.
Thanks, that was great. Can you go to your last slide?
Yes. There we go.
Okay. So is it Apollo 11 where you have the really bright, that's your little special Mario bit, or is it?
That's where we kind of lose the correlation between titanium and surface reflectivity.
So
So it's lower power than what would have been expected.
was there any difference between like the rock types connected to Apollo 11 and 12? If that's what is there something that you can test your theory against based on what they found at those two sites?
Yeah, so what I will say is that I've looked through the Apollo samples at the Mare basalt permittivities. Mostly the regolith is pretty consistent in permittivity, but the Mare basalt does vary a bit. And Apollo 11 they're ilmenite basalt, so they're high titanium, and they do have higher permittivity there than elsewhere. So yeah, it's interesting for sure. Yeah.
Cool.
I'm excited to introduce Julia Miller. Julia is an exchange student from ETH Zurich. She is working with Danielle Tuma, an equivalent of a fourth-year PhD student here, for the past 6 months, studying the pre- and post-conditions of wildfires in Central Europe. So we're going to go from the moon back to Central Europe. And I would also like to announce that today is Julia's last day here at UTIG with us. So give me a warm welcome and a good send-off for her.
Yeah, thanks, Michaela, for the introduction, and thanks, Constantino, for squeezing me in and sending out another email to all of you. Today, I'm going to present you the work I've been doing with Danielle and my supervisor, Manuela, on preconditions of wildfires and how they vary within Europe. And as a motivation, I show you here the fire event size of the 95th percentile of fire events between 2001 and 2020 for 8 different climate regions in Europe. And what you see here is that especially like in northern regions such as Scandinavia, Eastern Europe, and Mid-Europe, we've seen very extreme fire events in the past years. Whereas in Southern Europe, the past decade remarks very strong fire events. And therefore, we are interested into understanding what are the regional and seasonal characteristics of wildfires and their drivers across Europe, and what are the most important drivers of fire events. And lastly, I want to show a bit for how long these drivers have been persistent before fire events happened. And therefore, we are using 3 data sets. The first one is ESA fire CCI burned area product at daily levels. We use SARA reanalysis data for the hydrometeorological drivers, and to also get the metric for fuel availability, we use modus gross primary productivity for the time period of 20 years, from 2001 to 2020. And now first, I want to give you a bit of background on the seasonality in these different regions. But first, overall, here you see all the fire events we're studying, meaning the cumulative burned area over the past 20 years in each pixel's fire events. In total, we look into approximately more than 100,000 fire events. And if we scale for each region, the burned area to the seasonality, we see that we have quite different patterns. For example, in the north, we have spring fires, whereas in the south and in the Alps, we have a prominent summer fire season, which also prolongs into the fall season. But in the remaining regions, we have a rather mixed seasonality over all seasons. So this means we might have different drivers in these seasons. And therefore, we are looking into 10 variables, of which the orange ones are positive variables enhancing fires, and the bluish purple ones are deficit variables. We scale all these variables to unit variance to make the variable units comparable amongst each other. And in the next couple of plots, I'm showing you the seasonal anomalies where we subtract the seasonal mean from each fire day in correspondence to non-fire days. And this results in a quite complex plot. So I'm showing you one panel now to explain you how it works. On the y-axis, we have all the variables. And on the x-axis, we have all the regions sorted from left north to right south. And the variables which are positively enhancing fires, such as temperature, did not change their sign, whereas deficit variables such as soil moisture, we flip the sign so that a large number of soil moisture is fire enhancing, so to say. We also apply the U-test and to show like which results are significantly different from fire days in comparison to non-fire days. And if we now look into all panels for all seasons, we see that wildfires occur in all regions under seasonally warmer and drier conditions. But especially drought-driving variables such as vapor pressure deficit and the standardized precipitation index and soil moisture are the strongest pronounced variables on fire days when compared to non-fire days. If we look into temperature, temperature is not so strong pronounced, and surprisingly, especially in the summer, in the more southern regions, the difference is rather shallow. On the other hand, we find quite interesting that gross primary productivity is in a seasonal deficit in spring and summer, whereas in fall and winter, we have more gross primary productivity on fire days. Snow depth is especially relevant for snow-dominated regions such as Scandinavia, the Alps, and Eastern Europe. And we find that snow depth deficit is especially strong on fire days in comparison to normal days. Lastly, the Canadian Fire Weather Index performs well in all seasons and regions, which shows that this is a very good metric to address fire risk. However, we still don't know what variables are the most important drivers of wildfires. And therefore, we built random forest models to derive the feature importance, which is basically a purity measure of the tree splits in the random forest model. And here you see the results for summer. And you see the three most important drivers in all our subregions. We can basically divide Europe into two parts. The southeast shows that the GPP deficit and dry conditions in the SPI and vapor pressure deficit are the most important drivers. Whereas in the northwest, dry conditions in soil moisture and in air, such as vapor deficit, pressure deficit, are very strong. Further, we find in the more western regions, such as the British Islands, France, Mid-Europe, and Spain, hot and dry weather to be the most important drivers. In fall, this looks a bit differently. We see that fires are stronger drought-driven than in summer because the GPP deficit loses its importance and the standardized precipitation evaporation index gains importance. We can group the north and central western regions to strongly drought-conditioned wildfires, whereas we can group the southern Europe regions and mid-Europe to hot and dry weather-driven wildfires. Still, we do not know for how long these seasonal anomalies have been persistent. And therefore, we came up with the concept of anomaly persistence, which basically computes rolling windows over increasing window sizes from the day of fire, which is 0, to up to 1 year before a fire. And then you see that at a certain time step of this rolling window size, the graphs for fire and non-fire start to deviate from each other. And now the question is, when is this differentiation interesting for us? We decided to go with the variability of the difference between these two graphs and then map the two standard deviation of the difference on the no fire conditions to see when the fire conditions emerge this window. And this is the concept we prescribe on the next few slides on anomaly persistence. Here I'm showing you this only for 3 subregions from north to south. And we see that in summer, fires are very strongly drought conditioned, meaning that in the Alps and in the Mediterranean, drought conditions have been persistent for more than 90 days before fire events. And this propagates to the gross primary productivity deficit, which happens on a bit of a shorter time scales. We also find that hot and dry conditions, such as temperature and vapor pressure deficit, act on a sub-weekly scale, on a bi-weekly scale for less than 14 days. In fall, however, the picture changes again. We see that a GPP surplus is accumulated in spring by the very long anomaly persistence. And over the summer period, hot and dry weather dry out the fuel which was built up in the previous spring season. And this leads me to my conclusion. We show that fires have different seasonalities in different climate regions, but also the drivers are different. For example, drought conditions are the strongest pronounced variables, and GPP deficit on fire days in spring and summer are persistent, whereas in fall and winter, GPP is more pronounced on fire days. The most important drivers are in summer, the GPP deficit. In fall, long-term drought conditions are relevant. And this is also reflected in the analysis of our timescales, where we show that summer drought lead to GPP deficits, and in fall, GPP surpluses from spring lead to higher fuel loads, which increase fire risk. With this, I'm closing my talk and want to thank you for your attention. Wait, we need to get the...
Thank you. Very interesting. You did talk a little bit, I think, at the beginning of the fire weather index, right? And it sounds like it's not reliable, or I mean, there is no strong correlation with it. Could you just comment on that?
Yeah, the fire weather index is a very general metric to assess fire risks. It's very well correlated with burned area. But in this study, we want to focus on the ingredients of the fire weather index. So we want to show which variables are stronger pronounced, as the fire weather index incorporates like 4 variables, which are actually temperature, wind speed, precipitation, and a 4th one, relative humidity at once. So therefore, it's hard to say like which of these variables is the strongest. And therefore, we have this basically as a baseline to compare our results to, rather than a critic of the fire weather index.
Oh, thank you. I just want to ask, whether or not the wildfire can drive those drivers, like the wildfire will change the temperature, change the dry conditions, whether or not they are not drivers, they are just driven by the wildfire. Is it possible?
I think wildfires can create their own weather system when they're large enough, like clouds, and also like it is studied that during wildfires, temperature around wildfire starts because of the heat of the fires. But this is not the focus of our talk. We're like looking into what happens before a fire and not during or after a fire.
Okay, thank you.
Thank you. So you mentioned you're looking at the time period from 2000 to 2020, and you're looking at these annual seasonal changes. Are there differences on other timescales, for example, like longer term variability that you're able to see through your analysis?
That's a great question. Actually, it's hard to do this on a 20-year time period because some studies, especially for the very extreme fire events which happened, showed that pre-season conditioning was very prominent, especially like regarding fuel loads. But these are only 3 or 4 years out of the 20. And I think we can sample this variability with our observation data set. For example, if you have multiple drought years in a row, you don't have so much fuel built up in the springtime, which might lead to weaker fire seasons. Whereas if you have a humid springtime, you have stronger fuel loads, which exacerbate fire, risk of very large fires in the summer and fall season. But therefore, our time period is too short.
Thank you.
Thanks. Yeah, interesting talk. So, humans, is there any impact, any impact from, you know, civilization in this area, which there's been one for a while, on wildfire, especially over this 20-year period where we've seen lots of economic variability happening?
Well, that's a great question. I think fires in Europe are way more human influence than in the US because we don't have this large patches of unmanaged wildland. We're very densely settled over there. So most fires are ignited by humans rather than lightning strikes, which is also something we did not account for in this study because it's very hard to disentangle like the ignition source, if it's like a natural ignition source or an artificial ignition source. But yeah, we had to make a compromise and we canceled the humans out.
Great talk. I guess, have you looked at like the magnitude of these conditions and like clustering of events? So it's like, oh, if there's, you know, this much of a condition that's occurring, you may expect like a outbreak of sorts.
Actually, I'm not looking into this, but my colleague back in Switzerland started to look into the synchronous occurrence of fires and how drivers might lead like to large wildfire outbreaks, like in multiple locations at the same time. So I can't answer that, but it's a great question.